Now let's see how we can use spherical coordinates to set up a triple integral. First, we will need to know what the volume is of sort of a spherical wedge that is defined by a range of rho values, phi values, and theta values. And the reason we need to know this is because we're going to get an extra factor in our spherical coordinate integrals the same way that we had an extra factor of r in integrals that used polar or cylindrical coordinates. What I'm actually going to do is start with a slightly easier problem where you imagine you have a sphere of a fixed radius, say rho. We're going to take two lines of longitude on that sphere, and then two lines of latitude, and they define kind of an almost rectangular piece. And what I want to know is what is the area of that piece. Now briefly, these two lines of latitude, the two horizontal ones, the kind of distance between them, well, the difference between them is that they are at different phi values. So that distance we might call a difference of phi values. So that's the difference in the angle that sort of determines those two. And in the same way, the difference in the lines of longitude is a difference of theta value. Okay, so I'm going to blow that little piece up. So, you have some, vaguely rectangular shaped thing like this. Now, the boundaries of these are made out of pieces of circle. And if you want to know the length of an arc of a circle, well, in fact, this is one of the nice reasons that we use radians. You just take the radius of that circle and you multiply by the angle in radians. For example, if the angle were 2 pi, so it were the entire circle, then you'd get that the length is 2 pi r, which of course is the entire circumference. So all I need to do is figure out what the length is of these various arcs. Okay, so let's first look at the vertical arcs. These are arcs that come from these lines of longitude. And let's say that this is a sphere of radius rho. Well, then all the lines of longitude, they're all the same length. They all look like they're a part of a circle of radius rho. And we said that the length of this piece of this line of longitude right here is determined by a difference in phi values. So that means that the length of these little bits of longitude is going to be rho times that difference in phi values. So that's what that length right there is. Now what about this length? I should be a little bit careful in principle because the top length and the bottom length, they're not exactly the same because they come from different lines of latitude. But you could sort of average them if you really wanted to, and in the end, you would take the limit as the number of pieces went to infinity, and so it sort of doesn't matter to be too finicky about it. So you'll notice, of course, that as you move away from the equator, the lines of latitude get smaller and smaller. They're coming from circles of smaller and smaller radii. And indeed, if you're up at the North Pole, it sort of becomes just a single point. So the radius isn't just rho anymore. In fact, it's going to be rho times sine of phi. Well, one way to sort of convince yourself that that's probably true is to just think about the equator. The equator, remember, is at an angle of pi over 2. And of course, the equator is the largest one of these lines of latitude. And the radius of it should be the whole radius of the sphere. And that works out in this equation, that when phi is pi over 2, then you end up getting a radius of rho times 1, so just rho. Okay, so that's the radius. We said that the angle of the sort of top and bottom pieces comes from a difference in theta values. So this should be rho sine phi times that difference in theta values. So let's put that up here. Rho sine phi times delta theta. Well, this little patch isn't really a rectangle, but it's pretty close to a rectangle. And we're going to kind of approximate and just be confident that in the limit, as the number of pieces goes to infinity, these become enough like rectangles that the differences end up kind of washing out. And so the area is approximately just the product of this sort of height and this sort of width. And so you end up getting a factor of rho squared times sine of phi times delta phi delta theta. Okay, so that's the area of one of these little patches here, like a little patch you might see on an actual globe. Now, how do I find the actual volume, though, of a spherical wedge? Well, I've kind of taken care of the phi and theta inequalities, and I just haven't dealt with the rho inequality. And the basic idea is just that if you were to kind of think of your wedge, it's sort of, it's an almost box. And you can think of it as, you have sort of two spheres. You have a smaller sphere of radius A and a larger sphere of radius B. They each are going to have a patch like this on it. And so the area of those patches is going to be something like this. And well, if I have an almost box where this is the area of the base, and the height of that almost box, well, it's basically the difference in the rho values. And so you end up getting a volume, which is approximately the area from before times the difference in rho values. And so rho squared sine phi times delta rho delta phi delta theta. Okay, so how does this all actually work out in practice then when you want to do a triple integral in spherical coordinates? So to integrate some function f of x, y, z over some solid, well, you need to convert your function to spherical using the equations that x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine of phi. You have to set up bounds for your region D, and those bounds will be a range of rho values and phi values and theta values. And typically, if you're using spherical coordinates, you're going to do that in a situation where the bounds are probably all going to be constant. In principle, they don't have to be, but spherical coordinates really works very nicely for spheres and parts of spheres, and not so nicely for other things. Well, and then finally, you're going to change dv. So dv in rectangular coordinates is, say, dz, dy, dx, or possibly in some other order. But in spherical, it's not just d rho, d phi, d theta. Because of all this stuff that we found before, you get an extra factor, actually, of rho squared sine phi. Essentially what happens is that if you go through the whole argument of writing a triple integral in spherical coordinates, you end up taking the limit of a triple Riemann sum that includes terms like this here, and so that's why you get an extra rho squared sine phi. Okay, and then at that point you just integrate, and then you're home free. So next time I'll show you an example of how to actually integrate something in spherical coordinates.